Uh, so hello everyone, my name is Zach Schillaci. I'm a PhD student at Brandeis in the ATLAS experiment. And today I'll be talking about tracking performance with the upgraded ATLAS detector for high luminosity LHC. So already on the intro slide here, I won't spend much time here because there's already been a lot of talk about this, but this is all towards the ultimate run of the LHC, the so-called high luminosity program, or the HL-LHC. In this program, we'll be upping the center of mass energy up to 14 TeV and increasing the instantaneous luminosity. With all of this, we expect an average of, say, 200 interactions per bunch crossing. This is what we call pileup. So you can imagine this is a very dense environment for tracking. There's a few simulated event displays on the bottom at a pileup of 140 and a pileup of 200. So you can really see how dense these environments are. So of course, with these conditions, you could imagine that the tracking and the detector has to be upgraded to maintain high performance throughout this, what will be nominally a decade-long program. So on slide 3, this is sort of the purpose for the ATLAS Inner Tracker, which is a complete replacement of the current ATLAS Inner Detector, which is our current tracking detector, designed specifically for the high luminosity LHC. So with respect to Run 2, it has a finer granularity and improved radiation hardness to cope with the higher fluences we expect in high luminosity. It also extends the forward pseudo-rapidity coverage, I think I can show with my mouse, down to a pseudo-rapidity of 4, whereas the current tracking detector only goes out to 2.5 there. And its design is now all silicon, which consists of an inner pixel subsystem, which I highlighted here in red, and the outer strip subsystem here in blue. The pixel subsystem in red is what takes us down to this really far forward region in pseudo-rapidity. And they both consist of a combination of barrel layers and end cap rings or end cap disks. Now for many of the results I show, considering what we had as our nominal layout, which had a pixel pitch of 50 by 50 micrometer squared. But actually there have been some alternative geometry studies and alternative geometries that have been studied, and we've actually updated our baseline recently, which I'll mention later. On slide 4, continuing with the design of the ITK. So the layout is such, and it's designed this way to guarantee hermetic coverage within the full acceptance. So this means if you look at this plot here, we will get a minimum of 9 strip plus pixel hits on track for all particles above 1 GeV and PT, and within this C window here. So this allows us to tighten our track selections without compromising the efficiency, and we can therefore maintain higher efficiencies and a low fake rate. I also include here some details about the Run 2 tracking detector. What I mentioned before is that the acceptance here was limited to 2.5 in the pseudo-rapidity, which is now extended. And on slide 5, continuing a bit more with the design of the ITK and its layout, this is an overview of the material budget. And what we see here is I show a comparison of essentially the material versus Run 2. What's actually being shown is the number of nuclear interaction lengths traversed before satisfying the hit requirements. So Run 2 here is actually a uniform hit requirement of at least 7 hits on track. Whereas for ITK, we're actually able to tighten these, and it becomes a ADA-dependent selection, which I highlight down here. But you see that even with these tighter track selections, once we move out to this forward region above, say, 1.5, we see these rather large decreases in the material with respect to Run 2, so up to 50% when we get down to a pseudo-rapidity of 2. So this is quite nice to see. On slide 6, we take a look at the efficiencies and the fake rates. So this is comparing Run 2 at a pileup of 20 with ITK at a pileup of 200. So there's actually a factor 10 difference in these comparisons. Here, the efficiency is just the fraction of all reconstructed true prompt particles. This is shown in the top right plot for TT bar. And we see here that the efficiency is roughly comparable to Run 2. We maintain over 85% through the full coverage of ITK. But remember, this is a factor 10 difference in pileup, so this is already good to see. The fake rate here, continuing below, is the fraction of all reconstructed tracks which are unmatched to a true particle. And here we see some really impressive improvements with respect to run 2, where the fake rate decreases by, say, a factor 10, and this is with this factor 10 increase in pileup. So these improvements can be attributed to a few factors, such as the reduced material budget, which I just briefly outlined, but also the increase we have in the overall hit counts, sorry, which allow for the tighter track selections. Going on to slide 7, we look at the impact parameter resolutions. So on the left, we have the transverse D0 parameter, and on the right, we have the longitudinal Z0. These are all for single muon samples, but in the top row, we have a 1G VPT, which is low PT regime. And the bottom row, we have the high PT regime where the muons are at 100 GeV. So if we focus our attention on the high PT, where we're really seeing the intrinsic detector resolution, what we can see here is that the ITk D0 resolution, which is actually shown as either the blue or the green plot, this is just depending on the pixel pitch, is comparable to the run 2 D0 resolution, which is shown here in the black. You can see there is a difference depending on the layout of the ITk here. And so there is a possibility to recover this performance, and we do expect this to improve a bit from these somewhat outdated plots, given the recent reoptimization in the ITk layout, specifically relating to the inner pixel pitch and the inner pixel layer radius. And now focusing our attention on Z0, we actually see that regardless of the choice of pixel pitch for ITk, we already have some good improvements over run 2 in the resolution. And this is good because getting Z0 accurate is pretty important for pileup mitigation, which of course is an important issue for high luminosity. Going on to slide 9, a brief look at the vertex reconstruction. Here, vertexing is the process of both reconstructing and identifying the primary hard scatter vertex as well as additional pileup vertices. So of course, this is made more difficult given high pileup, where you have many nearby potentially overlapping vertices which you would want to individually resolve. So fortunately, ITk, thanks to both its hardware but also its software here, which we have updated quite a bit, we have significant improvements to vertexing, especially when we go to the high pileup regime. So we can start to look at the vertex reconstruction efficiency in the bottom left. You see again, there's actually 2 instances of ITk depending on the pixel pitch, but they're fairly similar in this case. And what we see here is when we compare with run 2, not only is the starting point already higher, but the robustness with pileup is much improved, so that when we increase in pileup, I should say this is the x-axis is the pileup density, it's just the vertices per unit length. So when we go up in pileup, we see that we're pretty robust in the reconstruction efficiency, whereas run 2 is shown to degrade. This is also reflected in the vertex resolution, which is just a measure of the position of the reconstructed vertex subtracted by the truth position along Z. And again, we see a similar case where ITk is much more stable with the pileup, whereas if we had stuck with run 2 detector and the run 2 algorithm as well, we would be losing performance here. And I should just briefly mention that they are using slightly different vertex finders. In essence, the ITk is a multi-vertex fitter, whereas the run 2 is doing this for single vertices. And going on to one of the last slides, slide 10, this is just a brief summary of the impact on physics objects. So there's a lot to show here, but from what I include, I think you could just summarize by saying there are really excellent prospects for future developments of both object reconstruction and combined performance for the high luminosity LHC, thanks to the ITk. If we start in the bottom left with pileup jet rejection, we see a comparison of run 2, which is shown here in the dashed lines, versus ITk as the solid lines. And here we see that the improvement is really pronounced in the forward region, mean, of course, here the run 2 is just limited to a pseudo rapidity of 2.5, but we see even in other areas we're improving over run 2. In the central plots, we look at the mu1 track isolation efficiency, which we see for prompt particles in the solid markers and also for background secondary particles in the open markers. And here what we see is this is here plotted versus the pileup density again. So here we see that the performance for mu1s above a PT of 30 GeV is already stable versus pileup. And this is if you look versus the pileup density, which is sort of a local pileup measure, or the number of truth pileup vertices, which is really the global pileup, how many vertices are in this event. So the prompt isolation is already fairly robust above 30 GeV, while the background rejection, which is harder to see, but it's down here, is essentially flat regardless of the mu1 PT, which is good to see. And lastly here for the B tagging performance, where we look at a comparison of run 2 in pink and the HL-LHC, which is actually sliced in eta, so the ITk there. What's important to note here is that there's again a big difference in pileup, so we're looking at about a factor 6 between run 2 and ITk. But even with this, we already see that the performance is fairly comparable in terms of B tagging efficiency. And I would say also that there's really large room for improvements using just ITk specific optimizations. Okay, so on the summary slide, so to summarize, the ATLAS ITk is well designed to cope with the HL-LHC and to actually improve in some areas over the inner detector. It's an all-silicon design which has a finer granularity and improved radiation hardness, also improved hit hermeticity. The reconstruction, which I didn't really cover here, but I think you'll see in some other talks, actually later in this session, is really optimized for high luminosity, and we already have some significant speed improvements over run 2, even with the higher pileup actually. And yes, so the physics prospects are looking good for many number of things, and just to say that the layout is still evolving, and there has been recent sort of a decision on the baseline, which will further assist us. And one other thing which I haven't mentioned, of course, is the high granularity timing detector, this HGTD, which is a forward timing detector that will be installed alongside ITk. And this will make possible track time assignment, which can further help us with pileup projection. But that's another talk, I suppose. So thank you.
Many thanks, Zach. Any questions? Please raise your hand. I don't see any questions. Okay, thanks a lot. Then you can